This set of notes is about concentration and cell potential. A set of notes has been provided for you. You know the drill. So when we talk about cell potential and the concentration of the chemicals that we have within a voltaic cell, it helps us understand the answer to this question. Do batteries last forever? Well, any of us that have ever been around or used a battery before, we know that no, batteries don't last forever. They eventually go dead. So why is that? Why do you have a battery that was able to power something for a while and then all of a sudden at the end of it, it's dead and it either needs to be recharged or it becomes unusable? Well, to answer that question, we need to start by reviewing what we've learned a few days ago. So if we start by talking about standard cell potentials, right? We learned how to calculate the cell potential of a reaction, of a voltaic cell reaction, by taking the reduction potential and the oxidation potential, adding those together. For this particular cell that we did the other day, we figured out that that was 1.10 volts. Well, when is that? Well, it is a standard cell potential, so it's when things are standard. So that means it's this the voltage that we have when each solution is 1 molar in the cell. Okay, well, what if they're not 1 molar? What if one is higher, one is lower, or what's going on there? Well, when we change those molarities or change the concentration of the solutions in our cell, the voltage is going to change. It's not going to be the standard cell potential anymore. It's going to be a different cell potential. All right. Second thing we need to know in order to be able to understand what happens to cell potential as you change concentrations is the idea of cell potential and free energy, as we talked about yesterday at the end of our notes. So we learned that for a redox reaction, we can find the free energy by using the equation negative N Fe, where this is the number of moles of electrons that are transferred. F is the Faraday's constant, and E is the cell potential. Okay, that equation, because it relates to Gibbs free energy, allows us to determine thermodynamic favorability of redox reactions, as we said. So again, we know that a negative delta G means that our reaction is thermodynamically favorable or spontaneous. Okay, well, how do I get a negative delta G in this equation? Well, the number of moles is always positive. Faraday's constant is a constant. So it all depends upon the sign on the cell potential. So if the cell potential is a positive voltage, it's thermodynamically favorable. It's a spontaneous reaction. In order to get, if we have a positive delta G, we know that that's not thermodynamically favorable. Well, how would we get a positive delta G here? Well, it would again depend upon the cell voltage. So if the potential is cell potential is negative, that's going to make delta G positive, so it would not be thermodynamically favorable. Okay, so that's a situation where we've got positive and negative of those. If you remember from our equilibrium unit, delta G is 0. That means we're at equilibrium. Well, how would I make delta G 0 in this equation? By making the cell potential 0 in the equation. So therefore, when the cell potential is 0, we know that the reaction is at equilibrium. So if I put those ideas together, we then know that if the concentration changes, the voltage is going to change. And when that battery is running, we know that the concentration of the copper ions are going down and the zinc ions are going up. Well, eventually, we'll get to a point where this reaction is in equilibrium. And as that reaction reaches equilibrium, Q is going to equal the equilibrium constant. Okay? The voltage is going to equal 0, and our Gibbs free energy is going to equal 0. So that's 3 different definitions of equilibrium we have now. Equilibrium can be when Q equals K, can be when the cell potential is 0, or when Gibbs free energy is 0. So qualitatively, we can describe what happens to the voltage under non-standard conditions by comparing the reaction quotient of a cell to the equilibrium constant of a cell, Q versus K, relative to the standard potential. So if I have a cell that is thermodynamically favorable, we know automatically that K is much, much greater than 1. Okay, right? We know that this means that the reaction is going to be moving, favoring going in the forward direction. Okay, at equilibrium, though, Q is going to equal K, and the voltage is going to be 0. Okay. Now, if we think about what happens with Q and the voltage at standard conditions, we know that Q is equal to 1 at standard conditions because it's going to be all 1 molars in the Q equation, right? So it's going to come out to be 1 at the end. And we also know that our standard potentials are going to be not equal to 0. The only equal to 0 would be a plain standard hydrogen electrode at that particular case, the She electrode. All right? So if a cell concentration is not at standard conditions, the voltage is going to change. How is it going to change? Well, if Q is greater than 1, then we are closer to equilibrium than at standard conditions. Okay, because again, if K is much, much greater than 1 and at standard conditions Q equals 1, well then if Q is greater than 1, that means that we're getting closer to K. That means we're getting closer to equilibrium. Okay. From our previous study, we know that if we're getting closer to equilibrium, that we can do less work. Or in other words, in terms of voltage, we can do less work. We can have less voltage. So the voltage of our cell is going to be less than what the standard voltage is. Likewise, if Q is less than 1, we're getting further away from K being much, much greater than 1. So in this particular case, then, we know that we're further from equilibrium. And if we're further from equilibrium, we can do more work. If we can do more work, that means we're generating more voltage. So the voltage of that cell would be much greater than the standard cell potential. So in terms of how we actually would produce that, well, then what we're thinking here is if Q is greater than 1, we're closer than equilibrium, which means our voltage is going to be less. So how do I equal Q? How do I make Q get bigger than 1? Well, I jack up B and I decrease A. So in other words, we would increase the amount of product that we have or decrease the amount of reactants in our redox reaction. Likewise, the other way, if we want to increase the voltage, we want Q to get less than 1, and the way that we do that, again, would be to increase the amount of reactants, which would make us bigger denominator, or decrease the amount of product. Okay. Sometimes people think of this like a Le Chatelier's situation, but it's not because the cell is not at equilibrium. So therefore, if we change the products or the reactants, the amount of those that we have, we are not disturbing a cell at equilibrium. We're starting away from equilibrium and doing stuff those ways. So when we talk about increasing reactants and decreasing products, we always want to talk about that in terms of Q versus K terms, not in terms of Le Chatelier's principle. All right, so that allows us to say that the voltage is greater than or less than the standard potential. But what about, can we get an actual number out of this? Well, we can. On the pink sheet, you'll find something called the Nernst equation. And the Nernst equation basically says that if we take the standard potential times 2.303 gas constant times the temperature times the log of the reaction quotient over the number of electrons and the Faraday's constant, we can end up with, we can get an actual number for E. Okay. Now, AP does not require us to actually do calculations using the Nernst equation. So why is it on our pink sheet? Well, they like us to be able to use it to mathematically explain what's going on here. All right, so for the purposes of AP, we only need to be described qualitatively, not quantitatively. And so we can think of it this way. If I increase Q, that means my log of Q is going to be going up, which means it's going to be ending up getting greater than 1. If it gets greater than 1, that means we're moving toward toward K, and as a result of that, the E overall is going to decrease. If my log Q goes down, it'll eventually get to a point where it's less than 1. And so as a result of that, as Q decreases, the E is going to increase because the log of Q will become a negative number, which again will take this whole term and boost it and make it positive. Right, so one last thing that's related to this is what we call concentration cells. One application is of non-standard cells is to be able to go ahead and create a voltaic cell in which the redox reaction that's happening is happening solely because of a change in because of differences in concentration. So we have the same electrode. In this particular case, we have copper on both sides. We have the same solution. We have a copper 2+ solution, so maybe copper sulfate solution in there, right? And what happens is you have different solution concentrations driving the redox reaction, okay? So and the cell operates until the concentration on each side is equal. So if you start with a case where one side of the cell has a much higher concentration than the other side of the cell, basically what you can do is you can get a reaction to be driven from the higher concentration to the lower concentration. So what happens in this particular case, the anode, where the oxidation happens, is where you have lower concentration. So you get electrons going from the metal electrode on the anode side through the wire, and as a result of that, it is oxidized into making more ions for the solution. On the other side, we have a reduction where the ions become part of the metal, and that then reduces the amount of copper ions in that solution. And this reaction will keep on going until the concentrations of both solutions are equal. In other words, until we reach equilibrium. So on the cathode side, that's where you have the higher concentration. Reduction removes ions from solution and decreases the concentration. That's what you need to know about concentration and voltaic cells.